Welcome back to Codex. Today's speaker is Clay Shonkwiler from Colorado State University. Professor Shonkwiler is an expert in differential geometry and its application to frame theory. Today, he'll tell us about an optimization-based approach to the study of special classes of matrices. Take it away, Clay.
All right. Thank you, John. And thank you to all of the organizers for, first of all, just for organizing Codex, which I think is a great resource for the community, and then also for inviting me to sully your seminar with my talk. And then if people want to look at these slides on their own screen, you can see the address on there. I also just posted the URL in the chat, which might be a little bit easier. All right. So first off, I just want to mention that so all of this is joint work with Tom Needham. That's why his name is listed first. And then some of it is joint with Anthony Caine, who was my former PhD student. So if you tune out after the first 60 seconds, the things I want you to sort of take away from this is that in the presence of symmetry, you can often use geometry to tell you that optimization problems are easier than you think they should be. And so I'm going to basically show you some examples where you have some, loss function you're interested in, where, some special matrices you like are the global minima of the loss function. And in fact, it turns out that you can just do gradient descent and you don't have to worry about anything. Everything's going to work out great. And that comes from sort of symmetry plus some geometric ideas. And then secondly, something we only realized fairly recently was like you could actually use some of this optimization business to tell you stuff about the topology of the space of special matrices that you're interested in. All right. So first off, I just want to sort of set the scene by convincing you that, well, okay, maybe this is sort of a silly thing, but everybody cares about special matrices of some form or another. Maybe you care about self-adjoint matrices. Maybe you care about unitary matrices. A common generalization of both of those are normal matrices. If you've forgotten, I'll give you the definition of a normal matrix on the next slide. But just to say, it's a self-adjoint matrices and unitary matrices and skew Hermitian matrices are all normal. And if you like sort of a nice characterization of normal matrices, they're exactly the ones which are orthogonally diagonalized. Now, for example, maybe you don't just care about self-adjoint, but you care about self-adjoint with a given spectrum. For example, you care about projection matrices, or which grand matrices of Parseval frames are projection matrices or scale I guess they are projection matrices. Or maybe you are interested in, matrices with fixed singular values. Again, you can sort of interpret Parseval frames as matrices with fixed singular values. Or, in sort of a frame theory context, maybe you want to fix the norms of the columns or maybe the rows. And so in the frame theory context, this would give you equal norm frames. And of course, many of us are interested in where you both do 5 and 6, you want, equal norm Parseval frames. So fix both the singular values and the row and column norms. Or if you think in terms of grand matrices, you fix the spectrum and the diagonal of the grand matrix. And then, with these sorts of things, I mean, this is maybe in some sense an obvious question, but you can ask like, okay, well, so for example, I like equal norm Parseval frames. Can I sort of interpret these as the minima of some nice potential or loss function or, whatever terminology you want to use? And moreover, can you, for example, just do gradient descent to get from some random starting point to some nice matrix that you like? All right, so the first part of the story is about normal matrices and also balanced graphs. So let me just remind you what a normal matrix is. So it's a matrix that commutes with its adjoint. So I'm going to be thinking mostly about complex matrices. So, it commutes with its conjugate transpose. And, just bring the two terms to the same side. That's saying that if I take the bracket of A with its conjugate transpose, I get 0. So this bracket notation just means, A star minus A star A. Okay, so these are the matrices which commute with their adjoints. So I can think of them as the things where this bracket A star is equal to 0. And so if I want a nice function where these are sort of obviously the global minima, I can just take the norm of that, or because square roots are terrible, take the norm squared of that thing. And so then it's very obvious that the normal matrices are exactly the global minima of this norm squared of the bracket of A with A star. And then a less obvious fact is that, in fact, those are the only critical points of this function. So, well, that tells you that, okay, if you do gradient descent, you're guaranteed to eventually end up at a normal matrix because there's no other critical points you can possibly end up at. And this is, we believed this for geometric reasons, but in fact, you can prove this in sort of a purely elementary way, like you can just sort of prove it by multivariable calculus. But it's kind of surprising because this function is not convex. In fact, it's not even quasi-convex. So it has this feature that the only critical points are the global minima, but it's not, it's not convex or even quasi-convex. This is a picture. The global minima are basically the two axes that you see here and there, and this is a restriction of this function to a class of 2x2 matrices, and the normal matrices. You see the symmetric ones and the skew symmetric ones in these two axes at the bottom. But you can see that the sublevel sets are not convex. And so, if you just, set up a gradient descent like this, so you have some starting point and then you just flow in the direction of the negative gradient, then the theorem that you can prove is that, the limit always exists and it's always normal. And in fact, this flow preserves the spectrum of the matrix. So, whatever the eigenvalues you started with, you're going to flow to a normal matrix with the same eigenvalues. And if your matrix happened to be real to begin with, the flow will stay real for all time. And so the limiting normal matrix will also be real. And so this is an interesting, the fact that you preserve these features is kind of nice. So there is in the literature, it's known exactly what the closest normal matrix in any given matrix is. But it has some unfortunate features, the most significant of which is that if your initial if you choose some, square real matrix, then the closest normal matrix may very well not be real. And so in a lot of applications where you would like to, get from a matrix to a nearby normal matrix, the closest one is actually not one you want because the problem is real and you don't want to go to a complex matrix, just even though that happens to be the closest one. So the fact that you preserve realness and then also, in fact, preserve spectrum is a nice feature of this flow. Okay. Now, again, this is a theorem you can prove, if you read the paper, our proof is, at least we're trying to make it, extremely elementary. But, the reason we sort of believed that this should be true came from some geometric ideas. And so, why would you believe a thing like this? Well, okay, so I need to say a little bit about symplectic geometry. And so the point is the D by D, any space of complex matrices is going to be a symplectic manifold. And the symplectic form, so in general, a symplectic form is some two forms. So it's supposed to eat a pair of tangent vectors and spit out a number in some alternating way. And this is how it is. So if A is some choice of D by D matrix, and then X and Y are tangent vectors, which you can also interpret as D by D matrices. And so what's the symplectic form evaluated on X and Y? It's minus the imaginary part of the Frobenius inner product of X and Y, which is just, of course, the trace of Y star X. And more generally, a symplectic manifold is going to be a smooth manifold together with something called a closed non-degenerate two form. So that's what this omega is. So again, a two form means it's supposed to be some bilinear thing, and it's alternating, and then it's also supposed to be closed and non-degenerate, whatever those things mean. But like the sort of standard example is just think about the plane with the standard area form. Or if you think of the plane as the complex numbers, you can also think of it as I over 2 dz wedge dz bar. And what does this mean? So what does dx wedge dy mean? Well, if I have a tangent vector, AB, and another one CD, because I'm a differential geometer, I'm going to write these in this sort of I'm going to write the standard basis vectors as d by dx and d by dy. And so I have AB really means A d by dx plus B d by dy. And then I pair that with C d by dx and D d by dy. And then what happens is the dx goes looking for a d by dx. It's the dual, basically the dual basis vector, if you like. And so whenever it sees a d by dx, it pairs with it and gives 1. And so the dx looks for this d by dx, and the dy looks for this d by dy, and that gives you a times d, the two coefficients. But you can also do it the other way, that this dx could look for this d by dx, and this dy could look for this d by dy. But because they're in the wrong order, you pick up a minus sign because this whole thing is supposed to be alternating. And you see that, well, what do you get when you do this? You're just getting the determinant of the 2 by 2 matrix given by your two vectors. And so in general, these two forms are, in some sense, like 2 by 2 determinants. Okay, so this is some special structure on certain manifolds. It's sort of a shadow of some sort of complex structure sitting around. And in the setting of symmetries, so now I say, okay, well, I don't just have a symplectic manifold, but in fact, I have some nice Lie group action on that symplectic manifold. So for example, in this case, I can conjugate D by D matrix by an element of SUD. And then this action, it turns out, preserves the symplectic structure, and even is a little bit more, it's what's called a Hamiltonian action. And what that means in practice is that I get some associated map formally from the symplectic manifold to the dual of the Lie algebra of the group. But in this case, I can just think of the dual of the Lie algebra as the traceless Hermitian matrices, D by D. And this map, satisfies some axioms that basically says it plays nicely with the action of the group. And in this case, the map turns out to be exactly this thing we've already seen, where I take the bracket of A with A star. So that's telling me that my function, which again was the norm squared of bracket of A with A star, is just the norm squared of some moment map. And these are incredibly nice functions and just some sort of, sense. So, Frances Kirwan, did a lot of work in the 80s showing and she wasn't the only one, but, she's maybe, her results are really the ones that were inspirations for us, is that, this type of function, the squared norm of a moment map, tends to be a really nice kind of function. And so when you see it, you can expect lots of nice things to happen. And this is really coming from connections between symplectic geometry and algebraic geometry, and in particular, something called geometric invariant theory. And so the idea here is that this SUD action was really sort of the maximal compact subgroup of some SLD action, some linear, some algebraic group action, and that. So in the world of algebraic geometry, you want to work with algebraic actions, and so this is some shadow of some algebraic action. And then the problem in geometric invariant theory is, let's say one thing you get out of geometric invariant theory is a way of taking quotients of varieties by algebraic group actions. And the problem that you encounter is that in general, these algebraic groups are non-compact. And if you just took the usual topological quotient, you would not necessarily get something that was a variety. In fact, it wouldn't even necessarily, you could get non-Hausdorff quotients and all kinds of sort of terrible behavior. So this is sort of a visualization of an action of the non-zero complex numbers on the complex projective plane. And what you're looking at is, okay, so complex projective plane, if you work in homogeneous coordinates, you have 3 homogeneous coordinates. Now, if z0 is non-zero, then you can rescale to make it equal to 1. And then this is sort of the z0 equals 1 plane, and it's a real slice, and it's just an affine thing or whatever. But you see that what this action is you're scaling sort of z1 by t and z2 by 1 over t. And so in the picture, you're scaling the x direction by t and the y direction by 1 over t. And here I'm letting t get big, but of course t could also get small and things would go the other way. But you can see what happens is that there's a generic orbit is one of these hyperbolas. But then you have 3 special orbits that are a little bit weird looking. So one is the sort of the x-axis minus the origin, because of course, if z2 is 0, then you're just staying on that, z1, axis, and you can get any non-zero element to that axis. And so you get this sort of non-closed orbit, which is the x-axis minus the origin. Likewise with the y-axis minus the origin. And then, of course, the origin itself corresponds to z1 equals 1 and z0 is 1 and z1 and z2 are 0. And those points don't move. So if z1 and z2 are 0, then you never move anywhere under this action. And the problem is that's a closed orbit, but those other 2 orbits were not. And in fact, it's in the closure of those other 2 orbits. And so if you tried to take a topological quotient, you'd be sad because you'd be like, okay, well, I have these non-closed orbits whose closures intersect and things are unpleasant. And so the idea, it turns out if you do this geometric invariant theory business, the quotient turns out to be CP1, which is nice. And roughly what happens is you say, okay, well, if I have orbits whose closures intersect, I'm just going to make them all go to the same point in the quotient. Another bad thing that can happen is, for example, if z1 is 0 and z0 is 0 and z2 is 0, then you get points that you have to throw away because they sort of can't be seen by invariant polynomials. So the invariant polynomials in this case are generated by z0 and z1 times z2. Because if you take z1 times z2, then the t's cancel, and that's going to be invariant under this group action. And so you take homogeneous polynomials generated by z0 and z1, z2. But of course, if z0 and z2, for example, are both 0, then all of those things are 0. There's sort of no invariant polynomials that can see anything. And so you also, it turns out, have to throw those points away. So it's sort of a fancy quotient operation, but at the end of the day, you get something nice. All right, so anyway, this is the whole sort of beautiful theory, and in particular, you can realize this in these nice settings. You can realize the quotient is sort of a limit of a gradient descent of this moment, of the squared norm of this moment map. So that's in some sense why one would have believed that this whole business would work to begin with. There's also an abelian version of the story. So of course, SUD is non-abelian. But if I just take the maximal torus inside of there, of course, there's many conjugate maximal tori, but in particular, just take the subgroup of diagonal matrices in SUD. So that's a copy of U1 to the D minus 1. So it's a D minus 1 dimensional torus. And so, of course, the whole group acted by conjugation. So any subgroup also acts by conjugation. And when I again, this is going to turn out to be a Hamiltonian group action, and the corresponding moment map is, well, instead of taking the bracket of A with A star, which was the moment map for the whole thing, I just sort of project onto formally the dual of the Lie algebra of this maximal torus, which turns out to just be the diagonal elements of these traceless Hermitian matrices. So you take the diagonal of the bracket. And so what do the diagonal elements look like? Well, if you think about it and work it out, you'll see, oh, well, the sort of ith diagonal element is exactly the squared norm of the ith column minus the squared norm of the ith row. Or I guess I have that backwards. The squared norm of the ith row minus the squared norm of the ith column. So that's what the diagonal elements look like. And so what you're getting here is basically the vector of these differences, squared norm of ith row minus squared norm of ith column. And so in particular, when you get 0, that's telling you that the squared norm of the ith row is equal to the squared norm of the ith column. All right, so what I'm going to do is now I'm going to interpret these things as the weights on the edges of some graph. So now if I take the matrix A hat, where I'm just taking the pointwise square of all the entries, assume these things are real for the moment. Then what I'm doing, this condition is saying, well, in A hat, the one norm of the ith row is the same as the one norm of the ith column. And so if I think of A hat as the adjacency matrix of some weighted directed graph, then I'm just saying, well, what are the rows and the columns? Well, what they're recording is the sum of the weights coming into a vector and into a vertex, and the sum of the weights coming out of a vertex. And so when they're equal, you're saying, well, the weights going into any vertex are equal to the weights coming out of that vertex in this weighted directed graph. And so when this is 0, you're saying that, well, I have some associated graph which is balanced in the sense that the weights coming in and the weights coming out are always equal to each other. And so these balanced graphs are nice. I mean, this is what you want, for example, if you're using a graph to model traffic, and the vertices are intersections or something. You say, well, the number of cars coming into the intersection has to be the same as the number of cars coming out. They don't just disappear or, have some source of cars, entering the intersection from nowhere. Or likewise, if you're thinking of, a sewer system or something, you want the water coming into a junction to be equal to the amount of water coming out of the junction. Okay. So again, you can say, okay, well, fine. So what if we like the ones where this quantity is 0 because they're the balanced graphs. And so I can define this function as just the squared norm of this thing. And so the zeros of this function are exactly the balanced graphs up to this sort of pointwise squaring business. And the same sort of thing is true. If you do gradient descent, you're always going to flow to a balanced graph. Some nice features are preserved. So not only if you start real, you stay real, which is good, because if you're thinking about weighted graphs, probably your weights are real. So you don't want to start with real weights and end up with complex weights. That would be bad. The other thing that's nice is that, well, in your adjacency matrix, if you have a 0 entry, that means there's no edge between those two vertices. And it would be bad if you started with some graph and then you started flowing on this energy and 0 entries turned into non-zero entries, because that means you sprout new edges. But that doesn't happen. So if an entry is 0, it stays 0 forever. And if some non-zero entry becomes 0, it will then stay 0 forever. So you can sometimes delete edges, but you can never grow new edges. If you started with some graph, you're going to get some graph with the same topology, or maybe some of the weights go to 0, so some of the edges actually didn't matter. But that's actually okay. It'd be really bad if you sprouted new edges, because you assume presumably that the topology of the graph is sort of imposed on you by whatever problem you're trying to model. So this sort of does really nice things in terms of graphs, and it's in this world of sort of balancing graphs, people are interested in what are called local moves, which means it really only depends on sort of vertex information. This is not quite local in that sense. It's sort of quasi-local in the sense that if what happens to the weight on an edge only really depends on what's going on, nearby. So at so your edge between vertex I and vertex J is updated by a multiple of sort of the weight difference at vertex J and the weight difference at vertex I. So your edge looks at the two, vertices that it's connecting and says, okay, well, this vertex has some amount of weight coming in and some amount of weight coming out. And whatever the disparity is, that's going to go into my update, and likewise for the other vertex. So it's not looking really far away in the graph. It's only looking at sort of the edges coming into the vertices or coming out of the vertices that your particular edge is connected to. So it's sort of quasi-local in that sense. So this is and here's some pictures. So there's a flow, starting with this graph, you run this flow and you get to that balance. So if you look now, the weights are all balanced at each of these vertices. One bad thing about this is that I've actually decreased the total weight on the edges. So I normalized it so that the initial weights sum to 1. And then at the end, the weights only sum to 0.569. And so again, if you're thinking of a traffic network or a sewer network or something, this is probably not so great because you're like sort of getting rid of some of the mass in the system. You probably would like to preserve the total mass. And this gets even more egregious if you have a tree, because what happens is all the weights just go to 0. So that's not so great. And so if you can restrict this function to the unit sphere in the with respect to the Frobenius norm on the space of matrices, and something similar still happens. If you start with something that's non-nilpotent, then the flow will now preserve the total weight. So the sum of the weights on all the edges will be preserved. The total mass of the system will be preserved. You'll still flow to a balanced thing. It will still, it still won't sprout any new edges. And if you started real, you'll stay real for all time. And so if you take the same graph that I showed you before, but now apply this weight or this flow that preserves the weights, then it does something like this. So you still get to a balanced thing, but now you've preserved the total weight in the system. And so this is a triangle graph. One edge this edge you can't see because the weight is very, very close to 0. This weight is very large, and this weight is sort of smallish. And if you run this flow, then you flow to the thing you kind of knew you had to flow to, which is where all the weights are the same, because the weight coming into each vertex has to be the same as the weight going. So even if you start with something which is sort of almost a tree, because this weight here is very, very tiny, you still, in fact, flow to the thing that you kind of knew you had to flow to. All right. Now, the thing we're not entirely sure of, this is, in some sense, a theory thing, but like, what are there any applications of this in practice? And so if people have ideas of how this sort of graph balancing could be applied to some problem of interest, I would certainly be interested in hearing from you either now or later. But now I'm going to sort of switch gears a little bit and talk about equal norm Parseval frames. But maybe before I do that, I should pause for questions or comments if there are any.
Is it okay if I just unmute myself?
Of course.
Hi, we haven't met. My name is Rosa. I only stumbled into graph theory recently. I've been looking at graphs where we put weights on the vertices, not on the edges. And these are directed graphs. So I'm curious, is anyone working on figuring out the connection between, say, frames or spanning sets or even oblique dual frames of subspaces when you put weights on the vertices, not the edges? Maybe you don't know either. I don't know.
Yeah, the short answer is no, I don't know, but that's a good question.
Thanks.
I was wondering, how do you do the flows here? Are you actually doing gradient descent, or is there a clever way that you can actually exactly do a flow, a gradient
So
flow?
I'm just doing like the stupidest, most brain dead, take a step, in the direction of the gradient and then do again. Like, so, and
Okay.
even with sort of fixed step length. So I'm doing something really dumb,
Okay,
but
nice.
I would love, um, to be able to come up with a thing where it's like, oh, you in fact are sort of exactly integrating the thing, or doing a much fancier approach to this. So I would love to do something
Okay. And in
which,
your intuitively, does that mean that there's going to be some sort of small error that's occurring
yeah,
because you're
oh,
not
totally,
exactly
yeah,
following the
yeah. I
flow?
mean, yes. So all of these things, like there's some small error, and really like, um, I so these problems are sort of very close, very similar to something called isospectral flows. That they don't exactly qualify under the sort of the formal definition of isospectral flow, but they're very much in the spirit. And it's known that isospectral flows are, for example, not they will break like Runge-Kutta or sort of standard, techniques. And so these things, I suspect you have to do something a little bit fancier to do them numerically than just sort of the obvious things, because I think the obvious things will break in certain
Okay,
circumstances. So
interesting.
I think numerically a little bit not so good. Um,
Okay, huh.
so yeah,
Interesting.
I would love, I mean, and in fact, I have this on my sort of slide at the end, but I would love to have a sort of um, numerically, um, well formulated theory of how to actually do these flows. That does not
Okay.
exist as far as I'm aware, but it would be
In
cool.
the in the absence of that, do you have any simple bounds on how a step size might break some of these properties? Like if if you want uh what is it, each entry to be real, is there some way in which, well, it's not going to have a large complex component,
Well,
or
the
do
real
some
is
of these
actually going to be
properties?
okay.
Okay.
Because your everything inside, like if your matrix is real, its gradient is going to be real, and so you're going to be stepping from a real matrix to a real matrix, and so that is actually fine.
Oh, okay.
Um,
Yeah.
the other features are, like the for example, in the earlier one where I say, well, the spectrum is preserved. Well, it's not actually preserved,
Yeah.
on
Okay.
the nose when you do this. Um,
Okay.
but again, like I'm not doing anything, at all clever, and so like I'm sure a real, numerics person could do a much better job.
Okay. Oh, good to know. Thank you.
Cool. Yeah. Thanks for the question. All right. So let me switch gears a little bit and talk about equal norm Parseval frames. And so for my purposes today, I'm only ever thinking about finite frames. And so I just am going to think of a frame for CD to be a spanning set. And then I'm going to package my frame vectors as the columns of some D by N matrix um, called capital F. And then my frame is going to be a Parseval frame if the frame operator, which is, in terms of the matrix F, just F times its conjugate transpose, is equal to the identity matrix. Or said another way, if I take the sum of the sort of scaled projectors corresponding to my FIs, then I get the identity matrix. And then I'm also interested in, not just Parseval frames, but equal norm Parseval frames, which means that, okay, it should be Parseval and also all of the norms should be the same. And I'm going to express everything in terms of the squared norm rather than the norm, but whatever. And if you want to be both Parseval and equal norm, then basically using the fact that the cyclic invariance of trace tells you that, well, the sum of the squared norms of the columns is the trace of the Gram matrix, but that's the same as the trace of the frame operator. which if it's Parseval is the identity matrix, and so the trace of the identity is equal to D, and there's n frame vectors, so these squared norms all have to be equal to exactly D over n. So it's not just that like the norms are all the same, it's like you know what they'd have to be equal to if they're all the same. And here's just pictures of two simple examples of 3 vectors in R2, and then of 12 vectors in R3 of equal norm Parseval frames. All right, and I'm gonna just pretend that everybody believes that these are things that you should like and be interested in and that are useful for certain problems, and just move right along to thinking about loss functions or potentials, or however we want to think about this. And so there's a very nice function called the frame potential that goes back quite a ways, where you basically just take the squared Frobenius norm of the frame operator. And if you restrict this function to the equal norm frames, so the spanning sets whose vectors all have squared norm equal to D over n, then the global minima of this function are exactly the equal norm Parseval frames. Of course, you have to restrict to something because otherwise the min is 0 and you just plug, let f equal 0. So, but if you restrict to this sort of product of spheres, which are the equal norm frames, then the equal norm Parseval frames are exactly the global minima. And then, Benedetto and Fickus proved in, 2001 or something that this frame potential has no spurious local minima. So all local minima are global minima. Now, there are other critical points. You can have saddle points, for example. So in this is a picture of the frame potential for basically 3 vectors in R2. And you see, so these sort of 2 basins of attractions corresponding to 2 different equal norm Parseval frames, but there are other critical points. There's this max up here, and then there's the saddle point down here. But the only local mins are these 2 global mins. And this is sort of in contrast to other sort of potential functions that tend to have, lots of local mins that aren't global mins and can even be kind of gross. So these are 2 other potentials, on unit vectors. I think one of these is the Tamis potential, and one of them is some other, P norm, or P frame potential or something. But anyway, you can see both of these have sort of local mins that are not global mins. But that doesn't happen in this case. And so Tom and I, along with Dustin Nixon and Soledad.vr, actually gave 3 different proofs of the Benedetto-Fickus theorem, one of which was in the spirit of what I've been saying, where if you do gradient descent, and you start with a full spark frame, so some frame where all of the maximal minors have full rank, then you will always flow to an equal norm Parseval frame. So, okay, something bad happens, on this sort of line of critical things here. But if you stay away from that, you just flow down the valley into these basins of attractions, which are exactly the equal Parseval frames. And then Tom and I had proved, a year or so later, that the same sort of thing works for fusion frames. I won't say anything about what fusion frames are because I'm not going to say anything further about them. But this was actually in the background of all this stuff. On the other hand, so this frame potential is squared norm of the frame operator, and if you restrict equal norm frames, the global minima are the equal norm Parseval frames. You can sort of go the other way around, where instead of taking sort of the squared norm of the frame operator, which is sort of going to give you Parseval things, you look at something like, well, in fact, it's the 4th power of the norms of the individual vectors. So this frame energy was originally defined as this way in the middle, but you can sort of see that, in fact, you're going to get this thing over here. And the proposition is that the equal norm Parseval, so if you take this function and restrict it to Parseval frames, then the global minima are exactly the equal norm Parseval frames. So this is sort of, you can sort of go either way. You say, okay, well, I fix equal norm, and then I try to look for Parseval as minima of something, or I fix Parseval and look for equal norm as minima of something. And Anthony and his PhD thesis showed that, in fact, the same sort of thing works. If you work on the space of Parseval frames, then you can just flow and you don't get trapped in local minima. You always flow to a global minimum, which are exactly the equal norm Parseval things. So it's the same sort of story. Now, our thought was it'd be nice to sort of not have these weird restrictions onto either Parseval or equal norm. What if you could do everything in one shot? And so you have the frame potential, which gets you sort of the frame operator. You have this frame energy, which gets you sort of the norms of the frame vectors. It'd be nice to sort of do both at once. And so you can essentially combine them in a special way. Now, you have to be a little bit careful because, of course, if you don't do something, you're just like, well, if I just sort of added these two things, I could just minimize it by just letting everything be zero. If f was zero, this would be zero, this would be zero. No, that's the smallest it can be. So you can't just take the squared norm of the frame operator. You take sort of the squared norm of the frame operator minus the thing you're shooting for, which is the identity. And likewise here, okay, so imagine that the R's are just all D over N, but they could be whatever you want them to be. You have some sort of target norms or squared norms of your frame vectors. That's in this vector R. And then you say, okay, well, I sort of want to shoot for that. And so in particular, you see, well, if Fj squared, the norm of Fj squared was equal to Rj, then I'd have 1 minus 1 is 0. So this term would be 0 if I was actually at, the desired norms. And of course, this term would be 0 if I was Parseval. And then it's, again, sort of obvious that the Parseval frames with your desired norms are exactly the global minima of this function. They're the only things where this function is equal to 0. And the nice thing is you have this, parameterized family. You can choose whatever R's you want. Maybe you want equal norm Parseval frames, but maybe you want some other R's, and you can choose whatever you want. And then it's the same sort of thing. Like, the theorem is that, okay, well, if I choose, the norms that I want, as long as they're what's called admissible, meaning that, well, there actually can be Parseval frames with those norms, then if I start with a full spark thing, I will flow to a Parseval thing with the right norms of all the vectors. And the energy, landscape looks something like this in one special case. Again, you have these sort of global minima, which are the only local minima. You can also have saddle points. You can also have maxes. But it's the same sort of story. So one thing I will point out that because of how we proved it, we used these sort of algebraic geometry things. We needed the R's, these squared norms of the frame vectors, to all be rational numbers. I think that's just I expect that the same is true if I choose irrational R's. But the way that we proved it, basically these R's turn into, choices of, weights on line bundles, and like there's no way to do this algebraically if those things aren't rational. And so if you actually do this, so this visualization is very simple. I'm just taking, two vectors in R1 and then just sort of plotting them as points in the plane. And if I do this flow, then what happens is I flow to the things that are the equal norm Parseval frames, where both vectors are, well, they're one-dimensional vectors. So both things are just like 1 over root 2, or 1 over root 2 and minus 1 over root 2. If I play this again, but I assign colors based on where things ended up, you can sort of see what happens is so it sort of you basically, the axes correspond where one of the vectors is the zero vector in the starting. And so those things are not full spark. In fact, those things are going to be what's called unstable in this world. And so the flow is bad on these two lines, but away from the lines, everything just sort of flows to what it's supposed to. All right. So now let me say something about topology in the last couple of minutes here. Let me give you a sort of brain dump of things that are known about the topology of spaces of equal norm Parseval frames, some generalizations thereof. So, this goes back to the frame homotopy conjecture from the early 2000s. And the conjecture was that the space of equal norm Parseval frames is path connected. And it took a surprisingly long time to prove this. So this was proved about 15 years later in a sort of very nice paper of Cahill, Mixon, and Strawn, where there's some technical mumbo jumbo, whatever, but basically the frame homotopy conjecture is true both for real frames and complex frames. And you have to play some games with, n has to be at least d+2 if you're real or whatever. But, fundamentally, the frame homotopy conjecture is true. And then Tom and I were able to sort of generalize this a little bit by showing that, okay, well, if instead of equal norm Parseval frames, maybe I pick the norms to be something else. Well, if I work over C, it's still going to be path connected. In fact, if I work with quaternionic frames, that's also true. If I can choose any norms I like, and the Parseval frames with those norms are going to be path connected over either C or H. And then Liviu-Mare in 2024 showed that the Parseval frames, the real Parseval frames with sort of chosen norms, is path connected for certain sort of special R. It's a little bit complicated, but if these things appear in certain special patterns, then it's going to be path connected. And then this is actually sort of slightly after what I'm telling you about. He showed that the complex Parseval frame spaces are not just path connected, but simply connected under a certain condition on the arms, that basically none of them is too big. So let me tell you how to get topology information from optimization. And sort of we have a theorem in the paper, which is very complicated. But what it basically says is gradient flow gives a deformation retract of the space of D by N matrices, which is, contractible. That's a very simple space, minus the things where the flow blows up, which is something that you have to get your hands on, onto these Parseval frames with your favorite, frame vector norms. And so let me give you another picture. So what you're seeing here is the orange is the bad set. Those are the things where the flow is not going to behave well. And then I've just chosen a bunch of random points. And then if you actually run this, then you flow to the equal norm Parseval frames. And so you see that the space you end up with is in fact connected. Why? Well, because it's a deformation retract of the complement of these lines in space. And of course, the complement of a bunch of lines in R3 is connected. It's not simply connected, but it is connected, and that's what you see here. And so in general, you taking some simple space, you're removing some stuff, but what happens is the stuff you're removing has high codimension. It has low dimension relative to the ambient space. And so you can't really disconnect things with things of high codimension. And so corollaries of this sort of meta theorem, for example, if you want to show that the space of equal norm Parseval frames is Q connected for some Q, well, what you need is that D should be at least Q+2 if you're over the reals, or Q+2 over 2 if you're over the complexes. And then N needs to be sort of sufficiently big.
Clay?
Yes.
So is the story that our space of frames has the same topology as K D by N minus UR?
Yeah, it's homotopy equivalent.
Yeah, that's cool.
Yep. And so, this is telling you not just about path connected, but, higher homotopy groups, again, under certain assumptions. And then, let's see, here's another thing. So thinking about real Parseval frames with given R's, what you can show is that if I start, well, there's a more general statement, but in particular, there's basically some open neighborhood around the equal norm Parseval frames where all these spaces are path connected. So it's so Dustin and Nate and Jameson showed that, well, the equal norm Parseval things are path connected, but this is saying, well, you can actually go out to some little neighborhood and all the things in that little neighborhood are also path connected. And again, you can start with not just D over N's, but a bunch of other stuffs. But so this is telling you that it's not just some isolated thing. There's sort of open neighborhoods where they're all path connected. All right. So that's what I wanted to say about results. And then just some questions that I have are, can we characterize exactly when these spaces are path connected? And the thing to keep in mind is that we know of examples where they're not path connected, even when D equals 2. There's a characterization of when some quotient is disconnected. And so, of course, if the quotient is disconnected, the original space also had to be disconnected. And so we certainly know of examples where these things are not path connected. We can also prove various theorems about when they are path connected, but there's no sort of sharp, if, it's either this or that. There's gaps between what we know about when it's connected and what we know about when it's disconnected. And then, of course, you could ask, well, what if I don't care about Parseval frames? What if I want, I want to specify different frame operators or different, spectrum of the frame operator? I expect a similar theorem to be true in the sense that you can flow, from whatever you want to whatever you want. But there's some technical challenges in trying to extend our proof to that setting. And then also a really interesting question is what happens when you can't flow to a Parseval, you've chosen your R's, your frame norms, but there is no Parseval frame with those frame norms. What happens? Where do you go? And sometimes it seems like you flow to, something that is still in some sense as good as you could do. And sometimes things seem to be crazy. So we weren't able to even formulate a conjecture about what happens, in that setting. And so this goes back to the question that was asked earlier about can these methods be made numerically tractable? We're not really implementing. I mean, we're doing this in sort of a very simple way, but if you're actually trying to do this at some industrial scale, you would want sort of better numerical methods. And of course, what other loss functions or potentials sort of fit into this general framework where you can just do gradient descent and everything. So anyway, that's it.
All right. I'm going to hit this reaction button.